approaches have been used elsewhere successfully, and they've been recommended by a number of, I'll call fancy committees, blue ribbon panels, nice way to say that, but a lot of people think this has great potential. Okay, so here's a nice picture of Fermilab. You can see we one time had the highest energy accelerator, the Tevatron, which is now passed the baton on to Europe to CERN as the highest energy machine. But we are now producing the most powerful neutrino beams in the world here, so we've been moving in the direction of high intensity rather than high energy. And so that, I think, has the greater application potential to the private sector than just going to higher energy all the time. So that's basically the strategy. So to carry out that mission, Fermilab designs, builds, and operates high-energy, high-power, high-reliability accelerators. And I would say in combination with Argon, we address quite a broad range of accelerators. We address different technologies, different capabilities, but in the end, I think we cover soup to nuts in almost everything that goes on with accelerators. All right, so at Fermilab, we build state-of-the-art accelerators to understand our world via particle physics. I'm not going to spend a lot of time discussing quarks and leptons to you. I'm sure you've already read up on that. So, but there have been many discoveries over the last 40, 50 years related to understanding basic nature using accelerators, and I think that's the message. We use them as tools of research. So that's all the particles that were discovered with accelerators. And in particular, if you go to this, we call these families, first family, second family, third family. Fermilab discovered the top quark, the bottom quark, and was the first to observe the tau neutrino. So 3 of the 4 in the last family were discovered here. So that's pretty amazing. Compliments to my colleagues in the past. Despite their impact on science, most accelerators that have been built are used for other purposes. So there's about 30,000 accelerators in use around the world. Sales, big number here. Accelerators touch a huge number of products in terms of their revenues or sales, and they're a major impact on our economy, in our health, day-to-day health, and well-being. So some of the products you see here are I'll go into a little bit of detail, but not too much. Hardening of tires, electronics, wrapping, various kinds, electron beam welding, and so on in the aircraft industry. So lots of applications that you probably haven't thought about. Okay, so accelerators are essential tools in industry. So ions are implanted into various metals to harden tools, reduce friction, materials for implants, to harden surfaces, modify optics, improve the quality of various gems. They're used in solvent-free printing, which is environmentally friendly, and the direction I think lots of people think we should be going. Food irradiation, I'm sure you're familiar with, and medical accelerators. Okay, so a wide range of industrial applications make use of low-energy beams of electrons. So electrons are used to drive chemistry. These are low-energy numbers for a place like Fermilab. We barely understand this lowness, but that's okay. But the megawatt is the challenge. So when you think about power, it's going to be the energy times the current, and so we're talking about high-current accelerators. So electron beam irradiation improves heat resistance of coatings, wires, cable. What we're seeing here is the electron is used to break the bond so that you basically form a new structure in the polymer so that you have a harder material, and that's what's used with radial tires. You can see there's 1,500 dedicated facilities around the world doing things like that. Okay, on this slide we're showing the impact of electron beam welding and machining, and it's used in all kinds of things, in your car, for example, in jet engines, in turbochargers. Roughly the size of a electron beam welding machine here in that picture by Pavlik. Accelerators are used for national security, so here you've determined that there's an old car sitting inside of this container, so that must be interesting to the government. More than 2 billion tons of cargo pass through U.S. ports and waterways annually, and accelerators are used for cargo scanning and active interrogation to detect special materials. And we've talked about using other particles than just X-rays, so there's
頂上を目指すもんじゃないですよ。もう安全は
more interesting things, I would say. Accelerators in medicine, I'm sure you're all familiar with proton cancer therapy, where you're using protons rather than X-rays. The seminal paper on this subject comes from Bob Wilson, who was the first director of Fermilab, who pointed this out as a possibility. And the first, I would say, facility-located machine was designed and built at Fermilab, and it's been operating on Loma Linda in California for decades now, working well. There's a worldwide industry in this now, and it's obviously had a big impact. So there's other technologies. People are looking at smaller technologies using superconducting technology to make things more compact, and this is still a very much a growing field. Okay, so that's what exists. Now, future accelerator applications are envisioned, so we give you a significant number of ideas that I would say that we've been thinking about. So there's the energy and the environment associated roles that you can use accelerators in, more industrial, medical, safeguards, and security. And I'm going to go through just a few of these for you. So, but one of the principal ones is the fact that accelerators can drive chemistry. So you're going to use the electrons from the accelerator to adjust the bonding of various molecules. The way it's done traditionally is that you heat things up, and it's a very inefficient process. And so you have to heat up the material or the gas or whatever to give enough energy to the system so that the bonds break, the electrons are ionized, and a chemical reaction can take place. Or you can use an electron beam to actually knock the electrons off, which is much more efficient. So that's the basic idea, is that you have a high enough energy electron to ionize the atom or the molecule that you're interested in modifying. So accelerators can be used for the environment. So here's an example with water. So they're effective for destroying pesticides, organics, pharmaceuticals. You can use them for sterilizing municipal water, for example, or sludges. It allows water to be reused, and of course water is becoming a super valuable resource. It's the oil of the future in some sense, so I see this as a potential significant growth industry. Beyond energy, the availability of clean water is the next crisis, and I think most of the planets figured that out already. Technology demonstrations are available, but they're not really deployed. And the question is why? Well, it's just the way we organize ourselves in municipalities. So a small township, say, would have to go out on a limb to put in such a sophisticated facility. So you need some kind of assurance that this is going to work. They're not going to be by themselves. So we think there's ways of working with multiple municipalities that this could be something that becomes quite practical. It should be reliable, could be compact, efficient, high power. So we're showing you in the upper right-hand corner the technology that Fermilab is putting a lot of effort into, as well as argon, and that's called superconducting RF. So it's superconducting material. It's a solid niobium that runs at cryogenic temperatures, and we think you can make compact systems using this technology that would be quite practical. Accelerators can be used for other things. So here you're seeing a picture of the night, satellite picture of the U.S. at night, and most of these bright spots are towns or cities. But this is actually the gas in North Dakota being burnt off. So we just waste it, basically. So many wells produce both oil and natural gas, but not all the gas is recoverable. The locations are very remote, so the pipelines are not very economical. They produce a burst of gas for only a few years, so that's why it's flared off. And as you know, methane is not good for the environment. So the worldwide business here, if you like, is 30 billion a year of gases flared, so it's almost unbelievable. It's equal to 25% of all natural gas usage in the U.S., and it's doing no useful work for us, and of course it's bad for the environment. There are techniques to deal with this, but these are very big, complex, difficult systems to put in remote areas. And so this hasn't clearly caught the attention of industry, and so has not really caught on to use. However, we think mobile accelerators could, in principle, be used to efficiently convert the gas to a liquid. So that's the basic idea. You would have a portable system that would maybe on a tractor-trailer arrangement like I show you here. So the trailer-mounted high-power electron accelerator. So I'm going back to the technology we're developing now. It's kind of state-of-the-art technology. The natural gas can provide the local power, and then liquid hydrocarbons can be created and can be mixed and collected with crude oil produced by the well. So there is a strategy to do this. I think it needs to be developed further, but has significant potential. And you can see the amount of single well flares in 1 to 2 years. So it's on the surface of it, it looks like it's a plausible business model you can put together. Coal, of course, is still a major source of electrical power in the world, sadly, I think. China and India are ramping up use of that. The U.S. EPA regulations will reduce coal, but it will remain an important energy source regardless. And so removing and cleaning emissions from burning oil is essential, removing the NOx and SOx, and there's techniques using electron accelerators again to be able to do that. And these techniques tend to use far less water than the traditional electrostatic separators. So these are other things we've been looking at. Accelerators for the environment, still highway life extension. So there's a lot of miles of paved roads in the U.S. Most of those are from asphalt. The average road, strictly in Illinois, undergoes lots of repairs and repaving every few years, and the U.S. places 550 million tons of hot mixed asphalt each year at a cost of about $25 billion a year. So it's a huge industry, and the heavy machinery used to rebuild the highways has a big carbon footprint as well. So even a technique that gives you a 1-year extension of life of the road would save enormous amounts of diesel fuel and taxpayer dollars each year. So you can think of this as, in an analogy to the way we've talked about radial tires. You radiate the tire, the molecular structure changes, and the asphalt becomes harder. And that's the logic. Now, it's not as trivial as that. You need additives to do this, but I think this is clearly something you can imagine has great potential. Again, it relies on the idea that you would need a mobile system, and we've gone through sort of a paper exercise here of how much you need, how fast you can drive, all those kind of things, how much value it would bring, and so we've started doing some real tests in this area to see how hard we can do it. So that's something we're just starting. Accelerator technology can be applied to wind turbines, so there are new materials like magnesium diboride, which we refer to as high-temperature superconductors. So these are materials that become superconducting at higher temperatures, which are easier to work with. There's been advances in these materials recently that allow them to have very high current densities, which then allow you to have high magnetic fields. And therefore, you can think about absolutely different approaches to wind turbines. And for me, the key thing is they don't have gearboxes. And so they're lighter systems, they're more efficient, and make a fair amount of sense. So I think there's another area we can get into a discussion about. So what's the obstacle? So I think the main thing is the risk and the high cost of entry. You need a lot of experts, you need a lot of understanding of these, I would call them advanced technologies. And so what we've started to do here, which is really a first for Fermilab, so Fermilab goes back to 1968, but I would say this is the first time that we've had a real desire to impact the private sector in what we do. It's the first time the Office of Science within DOE has had a similar attitude. So the idea of technology being transferred in a serious way has got momentum now, I would say. So we have built a new facility which we refer to as IARC, so it's the Illinois Accelerator Research Center. It was a joint project between the Department of Energy and the state of Illinois, and it's to enable Fermilab to work more closely with industry and university partners to develop new accelerator technology, demonstrate new applications, support accelerator education, to develop new accelerator technology-based products in high-tech industries in the U.S., and IARC is intended to be a portal for industry into the larger core capabilities and infrastructure of the laboratory. So the vision is well aligned with the goals of the DOE Accelerator Stewardship Test Facility Pilot Program, which you're going to hear about from Eric Gould. So as you drove in, you perhaps saw the building. It's a very nice-looking space age type building. We have a mission. We want to partner with industry to exploit technology developed in the pursuit of science. So for us to do world-leading science, we have to be at the cutting edge of technology. That's the simple answer to why we push technology so hard as we do our science. But we think that is going to have applications, especially in these portable, high-power electronic accelerators. That's really what we're focused on. So in summary, Fermilab is actively engaged in accelerator R&D in support of its basic mission, its science mission. The technology we develop, we believe, has applications beyond HPC. That's already true. Opportunities for lab industry university partnerships with transformative impact in manufacturing, energy, and environment. I give you a few examples. Opportunities to create new products and new industries. And the DOE is starting this new stewardship program, which we want to pay attention to and be involved in. And then there's other funding sources within the government that allows us to move these partnerships forward. So Argonne and Fermilab look forward to showing you our capabilities. You'll physically see them today and discussing possibilities for future partnerships.
Good
evening. Welcome to Fermilab. I'm Tom Carter, your host this evening. I'd like to tell you about some upcoming shows we have. We have one that's going to be very exciting that's not in the regular schedule. On Sunday, March the 8th at 2:30, we're going to have the Army Jazz Ambassadors. The concert is free. It's going to be great. But you're going to have to get tickets. So if you'd like to come to the Army Jazz Ambassadors, it's going to be here in the auditorium on March the 8th. Just call and get your tickets. So the next show after this evening is Saturday, February 7th. It's going to be Cirque Zuma Zuma, which is going to be an interesting combination of African traditions and modern-day circus. The next talk is going to be on the understandings of cancer on March the 13th, and that's going to be Dr. Minda Bessel from Lawrence Livermore. So that brings us to this evening's speaker. Everybody pumped up? Okay. Dan Hooper. Okay. So Dan completed his PhD in 2003 at the University of Wisconsin. He was a postdoc at Oxford, and then David Schramm Fellow here at Fermilab. Currently, he's an associate scientist with the Theoretical Astrophysics Group here, and assistant professor at University of Chicago. He's written more papers, can't count them up on cosmology and dark matter. He's the author of two books available on Amazon. Dark Cosmo, In Search of Our Universe's Missing Mass and Energy, and Nature's Blueprint. Okay, so if you're impressed so far, hang in there, it gets better. Dan is actually, an accomplished guitarist, right, when he was a postdoc at Oxford, he actually played in a band with Jem Finer of the Pogues. How cool is that, right? Okay. But here's the coolest part. Okay, Dan is actually in a blues band, the Congregation, who played here at Fermilab on this stage. So in the history of the lab, you are about to hear the only person that has both spoken on dark energy and played blues guitar on this stage. So please welcome Dan Hooper. That was ridiculous. Wow, quite an introduction. I don't think I can live up to this. So I just want to start by saying how cool it is to have this room filled. We live in a time and place where the common narrative you always hear is that the public's not really interested, and that you have to somehow trick or otherwise convince them to pay a little attention to it. Yet here we have 900 people selling out the joint. That's great. So especially all the young people in the room, I'm just thrilled to have this sort of interest in the science we're doing here at Fermilab. So I'm going to start by posing a pretty simple question, and then we'll get a little more complicated as it goes on. The question I want you to think about, and everybody think about, is just what is in our universe? Sounds like a very simple question. We all think we have some intuitive ideas about this. We might start by just looking around the room and seeing, okay, there's the stuff in the chair I'm sitting on, there's this wood that makes up the paneling, there's the clothing, there's the stuff that makes up my body, all this stuff. But that's just taxonomy. And what physicists are really interested in is trying to understand what all those things have in common. What are their smallest constituents? Why do they come in the patterns they come in? And how do they work? This is not a new question. This is an ancient effort to try to answer that question. So this is actually a diagram from the 17th century, but it depicts a much older idea than that. This is the classical Greek elements. We can see in the corners, there's the air, earth, fire, and water. This is alchemy as of the 17th century. This was, at that time, the best answer anyone had come up with to the question I'm posing here tonight. This is the elements as we understand them in the 20th century, the periodic table that you learn about in chemistry. And all that stuff I listed a couple minutes ago, that chair, your clothes, the wood, your body, it's all made up of stuff on this table. That's a remarkable accomplishment. All the stuff you have first-hand experience with, we can put on one chart. What's an even cooler accomplishment is the fact that everything on this chart is really just a combination of three things: protons, neutrons, and electrons. If you take those three things and combine them in different ways, you can make all the stuff we had first-hand experience with. And if you asked an astrophysicist or a cosmologist, I don't know, 30 years ago, what was the stuff in the universe, they would have pointed to this and said, probably it's mostly made of this. As far as we know, this is the answer. Mostly hydrogen and helium, in fact, a little smattering of other stuff. But if you ask the same collection of scientists today, they'll show you this line. And this is staggering. This is crazy, okay? All that stuff in the periodic table makes up about 4% of the matter and energy in the universe today. Okay, so most of that is hydrogen and helium out in intergalactic space, just in the form of free gas. A smaller piece, about 0.4% of everything, is in stars, planets, and other concentrated objects. Okay?
The other 96%, we don't know what it is. Okay? We use words like dark energy and dark matter, but the honest fact is we don't have much more than an educated guess about what this stuff is or why it's there, how it works. I'm not going to talk about dark energy today except for a few seconds now. We don't know what it is, but we know that the universe is growing or expanding at an accelerating rate. Whatever causes that, we call dark energy. We don't know why it's there, we don't know how it works, but it seems to be doing its job. And then the part that the part I'm going to talk about for the next hour or so is dark matter, which is kind of my area of expertise these days for these investigations. So, I'm going to frame this whole talk around questions. So the next question isn't what's in the universe, but now that I've told you that cosmologists think there's a lot of dark matter in the universe, I'm going to try to explain to you some of the reasons why we've come to that conclusion. Some of the earliest and most compelling evidence we have for dark matter's existence comes from the ways that galaxies rotate or orbit. So here's a picture of a galaxy, kind of like the Milky Way. This is what the Milky Way would look like if you got up above it and looked down. And each of these little dots are just a star or many stars. And just like planets orbit around a star and they are nearby, stars orbit very slowly around their galaxy. It takes about 250 million years, but the sun will go all the way around the Milky Way in that amount of time. A galactic year is much longer than the solar year. So this picture on the left is what a galaxy would look like and what the stars would do if there was no extra matter. So all the matter is the stars, gases, and dust that we see with telescopes. And then here's the same galaxy with a large amount of dark matter in it, about the same amount that we think the Milky Way has. At first glance, they look really similar. These look about the same unless you start paying really close attention. Look out here. See how slowly these stars are meandering. And then look out here. They're zipping around a lot faster. So the galactic rotation curves, as we call it, look really different when you put dark matter in a galaxy. And we see this in hundreds and hundreds of galaxies we study. We also see evidence of dark matter in bigger systems that we call galaxy clusters. The galaxy cluster is just a bunch of galaxies gravitationally bound to each other. The Milky Way is in part of a cluster we call the local group. It's not a very creative name, but that's one we start with. So this is actually a very special system. It's not just a galaxy cluster or a cluster of galaxies, but it's a pair of them. One here and one here. And about 100 million years ago, they underwent a collision and passed through each other. That gives us a very special opportunity to study the dynamics of these systems. I'm going to tear this image apart and show you one piece at a time now. So first, this is what the direction of the sky in question looks like in optical wavelength. So this is what it would look like if you just could look at it with your eyes. So it's invisible light. These bright things, they kind of look like stars, but they're actually individual galaxies. So these are all galaxies. Then this red or pink stuff, that's where an X-ray telescope detects light. So if your eyes see X-rays, you'll be able to see this part of the image. This part, this arc, or this bullet-like shape, that comes from the collision. So when these two clusters passed through each other, it created a shock or a wake, and that's the shape of this bullet. And then this part, these big blue blobs, are where we can tell most of the mass is. So basically, this is where the gravity seems to be located. You can see this by looking at how light is deflected around the system as it passes by the cluster. So let's put it all together. The interesting thing is the pink or the red, the hot gas, and gravity are in different places. So we're looking at an example where the gas collided with each other, slowed down, and the dark matter just kept going. You can pull apart the atoms from the dark matter, isolating them. And this is the first time anyone saw something like this. And it convinced a lot of people who had been skeptical of dark matter's existence that no, this stuff's real, and it's abundant in our universe. The third line of arguments I want to present is an explanation that dark matter offers for why galaxies and clusters of galaxies come in the patterns we observe. So the standard picture of the Big Bang, which is empirically confirmed in lots and lots of different ways that I won't be able to go into today, says that when the universe was young and hot, everything in it was pretty uniformly distributed. There was about the same amount of stuff everywhere. This is a dark matter simulation I'm about to run. This is what the universe looked like in the early universe. All these dots are a chunk of matter, in particular dark matter. And we're going to let that dark matter evolve through the force of gravity. And here we go. You can see slowly the dark matter collapses under gravity, forming dense clumps of stuff we call halos. And that's what it looks like now. These sorts of dots are individual galaxies, or halos around galaxies, and then the big clumps, those are clusters of galaxies, superclusters. The really remarkable thing is if I showed you this map, and then I showed you a picture of a map of galaxies that were actually observed in cosmology, in space, you wouldn't be able to tell them apart. These simulations predict what the large-scale structure of our universe should look like. And we don't have an explanation for that unless there's dark matter. And then the fourth and final argument I'm going to give as to why cosmologists have become convinced that dark matter exists. Give me a show of hands if you've seen this map. Okay. Yes, a lot of you, but not all of you. That's kind of what I expect.